Hello, everyone. And I will have a pleasure today to tell you about levels of high availability, and especially to focus how different high availability levels uh, high availability levels influence your architecture design. But let's start with a few words about myself. So I'm a cloud software engineer at Hazelcast. Before I worked at Google and CERN, I'm also an author of the book Continuous Delivery with Docker and Jenkins. And from time to time, I do training and speaking. But my main role is I'm developer on a daily basis. A few words about Hazelcast. So Hazelcast is a company behind three products: Hazelcast AMDG, Hazelcast Jet, and Hazelcast Cloud. We code distributed software and open source. It's all open source, and we actually a lot of our customers are like big enterprises, and they implement now multi-cloud, hybrid cloud, and so on. That's why I'm speaking about this topic. But this talk will be very general, very overview, but I will give you some examples of how we implemented some things in Hazelcast. Our agenda for today is, as you can see, pretty simple. So there'll be a very short introduction. Then I will walk through all high availability levels that you can implement in your system. So let's start from the introduction. So at the beginning of every system, there is always a service. This is our business logic. Sometimes we call it microservice. Some people call it microservice, even though it's huge. But actually, it doesn't matter if you call it a microservice, macroservice, or it's even a Lambda function. What matters is that this part of our application is stateless. And with stateless applications, we usually don't have any problems with stateless applications. Just imagine like if all our applications, everything we deploy is stateless. That would be just a paradise, because then you can deploy it everywhere in whatever instances you wanted and no problem with anything. However, that's not our world. Our world is that each stateless service has dependencies like data store, queues, some other services, some caching, a lot of different dependencies which are stateful. And in terms of high availability, it's data which is a problem. That is why this talk will be mainly about the data, about data stores, because all other things are way easier to make them high available. With this short introduction, we can move to the what I called level 0, which is a single instance. So single instance is actually not means your system is not highly available. It's like your developer environment. You run everything on your single machine, your application, your data store, and everything. You may think like, what the hell? Like, who would implement system this way? It must be some cowboy YOLO developer like doing some crazy stuff. But actually, there are some cases when you can use it, like some batch jobs, which can be repeated. So like in the idempotent batch jobs, or some other things that can be simply repeated. The good thing about single instance is everything is simple and the latency is low. I made a simple latency experiment. So I ran a single Hazelcast instance and measured like latency locally. And that is the graph for this. It will not tell you much. You can already see that latency is low, obviously, because it's run on one machine. So it's like 80 milliseconds for 10,000 of entries. But we will see later. Just remember this value, and you will see later how it compares to different availability levels. So a quick summary. So if you are not highly available, then obviously your system is not scalable, but from the good side, the latency is very good and the data is always consistent, and there is no such thing as a partial failures or something. So you are simply your system is not distributed. But okay, you didn't come for this talk to listen about non-available system. So let's walk straight into the first level 1 of high availability, which is multi-instance. Multi-instance means that if one machine is down, the system is still available. As simple as that. So this will be the diagram of our architecture. So we will have a request goes to the load balancer. It forwards to stateless applications deployed on multiple machines, and they use stateful data stores which are deployed on different machines. You can see on this diagram that the only single thing is a load balancer, but actually it's nowadays it's relatively easy to make load balancers highly available, like with multiple DNS entries, or so we will not speak here about load balancing stuff. We will also not speak about stateless part of the system because it's also quite easy to do it. We'll focus on the most difficult part, which is the data. So our assumption here will be we have two machines, we have two data stores. There is a local network connecting them, which is fast and reliable. As an example, it could be your data store can be deployed on two EC2 instances running in the same availability zone. You can consider them a local network. In reality, that is the one availability zone. So a lot of servers. By the way, this picture is taken from, I think, from CERN in Geneva, when I used to work. And if you are nearby in Geneva, actually, you can visit CERN. Not only their server room, but I used to be actually a CERN guide. So I walked the tours. You cannot see the Large Hadron Collider, but you can see a lot of different colliders, and so it's pretty interesting. But that is the one of the server rooms. So we have these two machines connected with the local network. So now we have to think how to make the data the same. We have to think about data replication. So let me tell you here a short story short history of the data replication. So you remember times SQL databases, they conquered the world, and people first used only one database instance. Then they thought, okay, we need to be highly available. So the first approach was let's create the same machine, and let's just copy the data from the one machine to another, like active passive data replication. So our services, they use only one machine. However, all the data is copied out to another machine. Then, in case of a failure, our services just fail over to a second machine. So we have high availability. And that is still a common strategy if you set up an SQL database, that you use active passive, or we can call it master slave. The difference is then the second machine is not only acting passively, but it also serves the data like read only. We can have obviously multiple slave machines. Then people found out that the performance is not good. So what they invented is like you can have sharding, and then each shard is replicated. So this is still a common approach in all these SQL databases. But in the history, at some point, people said SQL databases because of this ACID transactions, because of the relationships data, because of this SQL language, which is can be super complex. It's just limiting us for the performance. So they thought about no SQL databases, and then they invented clustering. So this is like clustering is how most NoSQL databases work. So the idea is a little different. So this time is every machine, every data store is the same. They just partition the data and each machine stored parts of the data. So each machine stored part of the data, but also backups of some other partitions. So if one machine is down, we still can recover the data from the backups of stored in other machines. So let me give you here an example just to understand it better how how Hazelcast works. So we partition all the data. Hazelcast is like a key value data store, in-memory store. So we store like we partition all the data into partitions, and each member, each node of our cluster, it contains some of the partitions. Like here on the picture, member 1 contains, for example, partition 1. Now, it is guaranteed that the backup of the partitions, pink on this diagram, the backup for partition 1 can be stored on member 2 or member 3, but never on member 1. So then if one of the member dies, crashes, what happens? We promote backup partitions and migrate the data partitions. So you are sure that if one member fail, one machine is down, we don't experience any data loss. And in general, it's like how NoSQL databases work nowadays. Now, the one question that remains here is, should we do it synchronously or asynchronously? In both cases, so whether if in case of the data replication like this SQL style or NoSQL style like clustering, should we do the backups synchronously or asynchronously? In other words, should we favor the consistency, strong consistency, or latency? You can think for a moment for yourself, which one would you choose? But let me here show the second latency experiment which I did. So I ran a cluster of four nodes in the local network on AWS instances of Hazelcast and measured the latency. And measured the latency for Synchronous backups, which is the default actually for Hazelcast. And you can see it looks like this. So it's you can treat this level 0 would be about like asynchronous data partition. This level 1 would be the synchronous. Here the synchronous may look like it's a very big number comparing to asynchronous, but still like 3,000 microseconds per 10,000 of operations, it's not bad. So it's still in most cases acceptable. That is why most NoSQL clustering would choose synchronous backup to favor consistency, like we do in Hazelcast. Obviously, you can configure this, but that is the default approach. Now, would it be the same in case of the data replication, or in case of the master-slave replication? I would say that depends. So, depending on the database, like MySQL, I think they do by default they do async replication. And that's because like this relational databases replication is quite complex, so it will take more time. That's why they favored async. But obviously, you can configure this. A short summary of level 1. So what if you deploy in multi-instance? What does it mean to you? It means that you can still have data consistency with reasonable latency. And actually, most tools support this level. And you can use a lot of cloud-specific toolkit like AWS SQS supports it. So, and the setup is very simple. Like no matter which tool you use, it's pretty simple to set it up. If you use cloud-specific tool, it's usually just one click in the console. But even if you would like to set it up yourself, the setup is pretty simple. From the downsides, obviously you are limited to one zone, and obviously you are if you deploy in one local network, if you would like to access your system from some other geo region, then the latency will be high. Okay, we covered the first, the level 1. Let's see what happens when we move to the multi-zone. Multi-zone means that if one availability zone is down, the system is still available. This is how availability zone looks like. So availability zone, usually it consists of a few data centers, but what is important is that each availability zone has a separate power supply, separate networking, separate connectivity to reduce the likelihood of two zones failing at the same time. So that is why we're invented. So usually they are close in a geographical region. They are usually connected with the fast network, but they are self unit. This is our diagram for how it would look like, the architecture for this. So it's pretty similar. It's just that we put our machines in a separate zones. Again, we will focus on the data, and you might ask yourself a question like, it looks very similar in cloud providers. It's sometimes just one click more. Is multi-zone deployment any different than multi-instance? And I would say no, but yes. So maybe why no? I did again the latency experiment to set up Hazelcast cluster across 2 availability zones on AWS, and here are the results. So the latency obviously is a little worse, but it's not much worse. It's not even 2 times worse if you set up your cluster across multiple availability zones. So it's still, you can use synchronous, strict consistency and synchronous backups on multiple availability zone. However, like I also said, it's a little different. And to understand why multi-zone is a little different than multi-instance, let's see an example. So we have our cluster, our cluster of the data. To give the assumption, so we have machines at least 2 availability zone, and the network is fast and reliable. For example, what I tested with Hazelcast was EC2 instances in two availability zones. Now let's come for a moment to the diagram we've seen before. So this is the Hazelcast and data partitions. So we are guaranteed that the backup partition is stored on a different member. But it may happen that, okay, the backup of the partition is stored on a different machine, on a different Hazelcast node, but they both may be in the same availability zone. And now if zone 1 is down, we lose the data. And that is definitely not what we would like to have. And we were thinking at Hazelcast how to approach this. The problem with availability zone that this is a concept specific to the environment. So we came up with the idea of a zone-aware feature, meaning that is how you specify it. So you specify in a Hazelcast configuration, group type zone-aware, meaning I would like my Hazelcast cluster to be zone-aware. Now, how do we deal that each environment is different? So we came with the idea of plugins. So they are also responsible for discovery and also for zone awareness. So if you run on AWS, you plug in AWS plugin, and then it queries the AWS native API to check in which availability zone my member is deployed. And like this, we can guarantee that the partition backup is stored in a different availability zone, which results in a drawing like this, that you are sure that if the partition if some data partition is on member 1, its backup can be on member 3 or member 4, but never on member 2 because it's in the same availability zone. So that is, I said, its deployment will be the same, but you make sure your data store supports zone aware. As a short summary, so I would say level 2 multi-zone, what does it mean to you? It's currently top 1 choice. So if you don't know what to do, that is the way to go, because it's relatively simple to set up. You still can configure this with synchronous communication, meaning your data is consistent. And a lot of cloud-specific tools actually support it. From the downsides, obviously, like if you deploy in one region, if you access your software from a different region, the latency would suffer. And not all tools are zone aware. So before you start a tool, or even like not cloud-specific toolkit is zone aware, just check if this is zone aware, because otherwise you may experience data loss. The next level, if you want to go one step higher, is multi-region. Multi-region means that if one region is down, the system is still available. That is our diagram. So we introduce a geo load balancer because we would like to load balance the traffic from the same region to end up in the same region, which to have better latency. The rest is pretty much the same. We just have to have 2 similar data clusters, and they need to replicate the data, which we will speak about in a moment. So we focus on the data. So our assumption is we have machines in at least 2 geo regions, and the network might be slow and unreliable. Because if we are talking about different regions, then the communication will use public infrastructure, which is very unreliable. Also, I know that AWS, they build their own infrastructure, but it's not, I think, don't connect all regions yet with that. But even though it's less reliable than local network. So another example, which I actually used, was to measure latency, which you will see in a second. I've set up EC2 instances in 2 regions. One was in Europe, the second one was in the US. So the thing about different regions is regions are far away, and we cannot change it. Like here is this is a nice tool from GCP when you can really interactively see what regions are covered. And if you see like from Finland to Oregon, it's 10,000 kilometers. So it's far away. It's far away even for the light, because like if you measure like the speed of light and the distance, you will see that if we send the light in a vacuum, it would be round trip time would be 60 milliseconds, which is already a lot, but it's in a vacuum. So it will be like at least twice or 3 times more if we measure this in the fiber, not in vacuum, not saying about all the routers in between and so on. So it's just slow because of the physics. That is why we need, in between our data stores, we need geo-replication. So we set up separate data clusters and use geo-replication in between them. So what is specific about this geo-replication, and why is it different than the normal data replication? So the difference is that it's always asynchronous, because it would just take too much time it would be too slow to support synchronous replication. And your data store must support it. So it's not obvious. Not all tools support geo-replication. And you must be prepared for the data loss because it's asynchronous. So let's describe. It's actually usually run in 2 modes, active passive or active active. In active passive mode, you have one cluster acting as read-only or not acting at all, it's just receiving the data, and the second one is write permitted. And the geo-replication is obviously asynchronous. That is why you may experience data loss, and you may experience consistency, like lack of strong consistency if you read from the receiver cluster. In case of the active geo-replication, it's even worse, because like we can write to both clusters, so we can experience data loss. Again, we have to be prepared for eventual consistency, but also we need a conflict resolution. What happens if two applications modify the same data at the same time in different data clusters? So like how most tools address it, how we also address it in Hazelcast, is that we have some conflict resolution strategies. You can define your own, or the most common one is actually the last one wins, but you have to be prepared for that. So in case of Hazelcast, we call it not a geo-replication, we call it WAN replication, but the idea is still the same. You have clusters in two different locations. And Hazelcast is actually very simple to configure. With that simple configuration, it will send the data to another cluster. So you might ask yourself a question, but I would like to have like I would like to have data clusters in two locations. So do I really need to lose consistency? And let's do another latency experiment. So what I did is first I've set up Hazelcast cluster across different geographical region. So I've set up a consistent cluster across region, like 2 members were in US and 2 members were in Europe. So you remember this was the diagram from before. So how big the latency will be? Think for a moment. What would be your guess? So I did this experiment yesterday on AWS, and that was the latency for multi-region. So it was way higher than multi-zone. It was like more than 100 times more. And as you can see, this latency is not acceptable. It's usually like it's useless. That's why people wouldn't. That is the reason why people wouldn't set up a cluster across multiple geo regions. That is also why you cannot spin up a Kubernetes cluster across multiple regions. While if we route geo-replication, obviously it would be the latency will be the same as multi-zone, because we pass everything asynchronously. So now you may ask, like, but come on, like some banking system, they need to have like consistency across multiple regions. And that is true. That is true. You still can have strong consistency in multiple regions. If you're interested in that, I would recommend you reading about something called New SQL, which is basically the idea of spanner, and CockroachDB is kind of an open source spanner version. So read how they do it. They do some tricks, but still it's a trade-off between consistency and latency. They also implement some consensus algorithms, so that if you have your data centers in a lot of regions, then not all of them have to agree on the same value, but just the majority. And there also you can have distributed transactions, but it will always be a trade-off between consistency and latency. Short summary of the multi-region. So you are super high available from whatever region you access your data. Latency is low. Sometimes possible with cloud-specific toolkit like Google Spanner, but actually most cloud-specific toolkit won't support it. And from the downside, it's geo-replication. It's just difficult to not depend on your data when it's sent asynchronously, and to depend on eventual consistency and conflict resolution. It will impact how you design your application, your business logic. That is why it's way more difficult than multi-zone. Okay, let's move further. Now, a lot of companies are moving to multi-cloud. So multi-cloud is it's like this. If one cloud provider is down, your system is still available. So this is a diagram. So it actually looks similar to what we've seen for multi-region, because we have some global load balancing to different environments. And obviously we need to replicate the data. So the assumptions here are like machines are at least in 2 cloud providers. Network again can be very slow and unreliable, and machines may be in different geo regions. So for example, like EC2 instances in European region and GCP VM instances in US West. So you may think like, how is it different than multi-region? Does it change anything? Because actually it's pretty similar. Like the replication needs to be asynchronous. They can be in different geo region. What's different? So there are some differences. So first thing is that you cannot use cloud-specific tools. Like you cannot use just Spanner and say, okay, spin up across multiple regions, because then you are not cloud agnostic. Also, you cannot use like VCP peering across different cloud providers, which will slow down your latency, and it will make your security more difficult. And obviously, it will really increase the cost of your infrastructure, because you have to pay not only AWS but also to GCP. So you may say like, but why people do it? Is it like the only reason is highly available? Am I really that afraid that the whole AWS will be down? Obviously, no. Like these are the main reasons why people do multi-cloud. So you implement multi-cloud to avoid vendor lock-in. So you don't want to be only so AWS specific that you will never change AWS. So you design your application to work on any cloud provider. You make this abstraction. This will also help you with the cloud cost optimization, because if you are already deployed on AWS and GCP, guess what? You can negotiate price better, because guess what? The prices of GCP and AWS are not the same for me and are not the same for big enterprises, which usually use multi-cloud. They can really negotiate the price. And the same is with risk mitigation, that they just use different cloud provider, because if for some reason AWS cannot work anymore in Asia or something, they can still move to GCP. Another thing is low latency. If your service will be accessed from application from different cloud provider, then you can reduce the latency this way. Also, like data progression, regulation compliance, this is probably clear that, and also the best fit technology. So you may use some cloud-specific portfolio for your system. Short summary, like the biggest thing is like you are no vendor lock-in, and you can negotiate the cost better. But the setup is complex, and you cannot use cloud-specific toolkit. So it's like a step further from multi-zone and multi-region. And the last for today is hybrid cloud. So some people even say it's hybrid cloud is the same as multi-cloud, but it's not the same. Hybrid cloud means that that part of your infrastructure is on-premise. So we could say, if all cloud providers are down, my system is still available. But you may say, like, really, is it possible that all cloud providers are down? Like, I don't think it's even possible that the whole AWS is down. So the answer is no. That's not the reason why people will use hybrid cloud. So the reason for hybrid cloud is usually some data requirements regulation, Like you cannot store some secret data outside of your really physical building. So you set up your own on-premise servers. So it's all about compliance, regulation, data security. One of the other reasons is that if you are already on-premise, but you would like to move to the cloud, so this can be a process. For some cases, also cost reduction, and the other reasons are the same as we already mentioned in a hybrid cloud. How it looks like? It looks like that we have global load balancer, which load balances the traffic to multiple cloud providers, but also to your on-premise infrastructure. Obviously, like it's super difficult to manage this. That is why in all our customers which are dealing with such strategies, they make some abstraction over the infrastructure, and this abstraction nowadays it's Kubernetes or Kubernetes derivatives like OpenShift or IBM Cloud. So you have at least the layer of abstraction, and you can address everything to Kubernetes, because otherwise you would be lost to deal with different cloud providers and your own on-premise infrastructure. As a short summary, so hybrid cloud is mainly if you don't want to be cloud lock-in, and also for low latency if accessed from some custom network. But the setup is very complex, and it usually will cost you a fortune. So it's like really for big enterprises, and but people are really doing this, or at least they are that's their target. So this way we covered like all high availability levels which you can use. So as a short summary, I will maybe not say anything I already said before. What I would like to show you is like how I see like complexity graph across different high availability levels. So at the beginning, we have single instance, which is super simple. But then if you would like to go from single instance to multi-instance, it's already difficult because you go from a non-distributed system to a distributed system when you have to replicate the data. Then going from multi-instance to multi-zone, it's actually quite easy. The complexity not increases much. You just have to have your tool needs to support zone aware, and you're pretty much safe. But then if you would like to go from multi-zone to multi-region, it's a big step, because you have long distance, which means you need to have asynchronous replication. Then another big step is from multi-region to multi-cloud, because you cannot use cloud tools. And as a last step, hybrid cloud is super complex because you have to own the infrastructure, which is another level of complexity. So which high availability level is for me? That would be super simplified, but I think if you are a normal guy and you don't know, then this is your highly availability level, because it's still simple to set up. It's pretty secure, and you'll be fine with that. If you're a Cowboy developer, obviously you can use no high availability. Then multi-region is mostly if you go global with your service. So if you would like to have low latency from different geolocation. And multi-cloud and hybrid cloud are for guys like for banks, for guys with the really strong security concerns and with really strong, with a lot of money and really security restrictions. And with this last slide, I would like to say thank you for listening. It was nice talking to you. I will check now if there are any questions on the Slido to me. Since there are no questions, I'd like to thank you once again for listening to me.